Hey, so here we're going to talk about what a binary search is and why they're useful. So a binary search is a search on data that's looking to see if something is in a list of information. There is one prerequisite, and that is that the list needs to be sorted to be performed with a binary search, because a binary search requires the data to be in an order. As you'll find that obvious when we start to do it, because it's clear that it has to be that way. So that's the only thing I can think of in the test. So the three questions I can think of in the test are: one, why they'll show you some data and they'll say, why is a binary search not appropriate for this data? And it'll be because the data is not sorted. Two, they might say, why is binary search considered a very fast search, or something about that? And the reason a binary search is a very fast search is because every step of the search you halve the data, which we'll demonstrate in a second. And the third one they'll ask is probably to show you performing a binary search. That's probably what they'll ask. So I'll show that to you now with this data. Notice the data is sorted because it has to be. Right, so what happens is, first step, we go to the middle. Now the middle here would be in between these, so we go to the left, because that's just what you do. So step one is we look here. And then the process is, what you do is you go something like, isn't the value 255 is smaller than 255, so we can eliminate the left data. Okay, so we know that the data on the left is dead. So then we draw a line or whatever through the data. Okay, and then we repeat this. So we bring this down here, go to the middle, left. I'm going to drag that down because it's the same thing as before. Isn't the value 255 is smaller than 255, so we can eliminate the left data. So eliminate this, and then we're left with 2. Look at the middle to the left. Isn't the value 255 is larger than 255, and there is no data on the left, so the value is not in the list, or something like that. So the value is not in the list. I'm going to put that there. And then that would be the end of the search, because there is no more data to look at, because you would just be going around in circles. So isn't the value 255 is larger than 255, and there's no data on the left, so the value is not in the list. Okay, so that's one example of me performing a binary search. I'm going to do a different one now. I'm going to use words as well. So I'm going to go Adam, Barry, Gary, Neil, Mary, Olive, running out of words, Paul, and Sarah, whatever. Okay, so random names. There we go. I'm just going to spread those out because I have to. For some reason they're not actually lined up. But anyway, we'll leave it. So, so basically, there you go. So there are the names, okay? I should have kept that arrow from before, so I'm going to very quickly draw the arrow again. There we go, that'll do, whatever. So I've got my arrow ready, because that was annoying. So there we go, we're going to search for Olive. No, we won't. We'll search for Mary. Okay, so the search is for Mary. So we bring it down. We look in the middle to the left. Okay. Not Mary. Mary comes after Neil. So we can eliminate the left data. Okay, once again, nice and easy. Draw the line through. Go on to this one. Right, so bring them down. Put the middle left one. Not Mary. Mary comes before Olive. So we can eliminate the right data. Or the data after, if you want to say that. Actually, it might be better to say that the data after. Data before. Might be better words to say, just to sound a bit more technical. But either will get you the marks. Right, so then we go no to these ones. Then we copy down what's left, copy down the fact that we're going to look at it, and then say Mary found. And there you go, that's the end of the search. So you can see why it's a fast search, because it basically halves the data every time. Thus meaning, like, even if you had, like, think about it, even if you had 1,000 things to search for, it's 1,000, 500, 250, 125, 62, 63, and then 30. Before you know it, only like sort of 5 or 6 searches, you're down to 30, 15, 7 maybe, and then 4, 2, 1. So, or 3, whatever, depending on the rounding. So, you can see that it can really cut down the data quickly. It's an inverse power of 2, really, when you think about it. So there you go. That's a binary search. Okay, so in this section, I'm very quickly, because it's not a very complicated part, just going to talk about linear search. A linear search is what you can do if the data isn't sorted. There isn't really a lot of options when the data isn't sorted, because if the fact is that the data is completely random, then there's just as much chance of the data being anywhere as anywhere else. So the only real search method you've got left is to go through one at a time looking at them. It's not I can't see them asking you this in the exam because it's just so easy. The only thing they might say is suggest an alternative search for this data. So they might say, here's some unsorted data, and say, why isn't a binary search good? And suggest a search you could use. So you would say a binary search couldn't be used because the data isn't sorted, but you can use a linear search. But a linear search is, just basically where you just go through each one and see if it's there or not. I mean, it's not a good one, really. So basically, you would go like that and then be like, not found, not found, not found. I mean, I can't see them doing these steps, because you would literally just be going down like this. In fact, I'm going to change this to olive to speed up the process, because I don't want to do 20 of these. There you go. I'll do 3 because we know it's going to be 3 because we've already got it. So basically, you would go like this. You might say out. Super. Good. Not found. And then you'd go found. So it's not very difficult. That's what a linear search is. You just go through the list, checking to see if it's found, and then that's it. I suppose the only other thing they could ask you is, like, what's the average kind of like length? Well, obviously, if how long would it take? Well, it would take basically, you take the number of elements plus 1 and then divide it by 2. So obviously we've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the average here is going to take 4.5 steps, because it's 9 divided by 2. So you just add 1 on. I really don't think they'll ask you that. It's not listed anywhere, but just understand that it basically takes, you add 1 to the number of elements, because you've always got to do 1 search. You see, that's why you add 1. So you add 1 to the number of elements and divide it by 2, and that's the average number of searches. Because think about it, we've got a number between 1 and 1, 2, 3, 4, 5, 6, 7, 8. So, the odds are it's going to be in the middle here, which is 4.5. So you add 1 to the last number, divide it by 2. If we only had 4 things, then the average would be 2.5, because, if we had 5 items in there, it would be 3. Because the odds on, that's the average one. So 1 search, 2 search, 3 search. And you work it out by doing the number of elements plus 1, and then you divide that answer by 2. But I don't think they'll ask you anything like that. But it's just good to compare that to, say, the binary search, where, if we had 1 million elements in a binary search, it might only take us, say, I don't know, I'm guessing, because I don't know a power of 2 for 1 million, but probably something like 22 searches to, I could Google it. What's 22 to the power of 22 to the power of, 2 to the power of 22 is 4 million. So actually, what's 21 then? 2 million, obviously. Yeah, so it would take roughly 20 searches to, in a binary search, to do 1 million. And obviously, it would take on average 500,000 on linear. So, you can see the difference. But there you go, that's linear search.